Good evening. I'm sure you're getting ready for the beer and gear party in another 1 or 2 hours. Coincidentally, this is a session on beer, but this is a different type of beer. We did Explicit Replication. I'm Nagendra from Cisco. This would be our agenda for today's presentation. We'll look into what challenge or what problem beer is trying to solve. What is beer? The control plane and the forwarding plane semantic associated with beer, followed by the use cases and the current standardization efforts. So before jumping into beer, let's pause for a minute and see what problem beer is trying to solve. So with current the multicast architecture based PIM-based or MLTP-based, it basically uses event-triggered tree building concept where the receivers are required to build a tree towards the source or the rendezvous point, creating a lot of state entries, data plane state entries all along the path. So it's not just data plane state entries, even for the multicast control planes like PIM or MLTP, in order to create, establish, and session, maintain a lot of control plane state state entries are created and maintained in the all along the network, which eventually leads us to scalability related issues. Now, the current multicast architecture does not provide a very efficient way of controlling the path over which the traffic can be steered across. We can't efficiently distribute the load, the multicast load in different part of the network. Another problem is poor path resiliency. So whenever there is a link or a node failure along the path, the downstream router is expected to detect the failure, recompute the path, rebuild the path, and start receiving the traffic. So technically speaking, it's not FRR, which is convergence within less than 50 milliseconds. Now, on top of all these challenges, the current multicast architecture is not really ready for software-defined networking. For those, I'm sure you might be aware of software-defined networking, but in a single line, it's more like having a centralized intelligence to control the network. Now, the current architecture is not ready for that. So the answer here is beer. Beer is trying to solve this challenges. The primary goal of beer is to eliminate the state entries, the control plane and the data plane state entries from the transit devices, and move the data plane state entries directly to the packet header, like what we do with segment routing. How do we do it? From a control plane point of view, it requires a unique assignment of bit positions to different edge devices which are connected to the receivers and propagate this information through IGP protocol extensions. From a data plane point of view, we encode the set of receivers directly in a bit string, which will be carried in the packet header. So basically, the bit string will identify the set of receivers who are interested to receive the stream. So this way, we carry the state entry directly in the packet header. We'll look into more about how each of these semantic works. So like I said, the very first thing for beer is to assign a unique bit position. So this is an example with a bit string of size 5. But in reality, we could have more, like 256 or 512, 1024, or even 2056. So going with this example of a bit string of size 5, each of these bit positions will be uniquely assigned to each of the edge devices which are connected to the receivers. Again, this is bit position assignment and not a binary assignment. So we call this as BFR ID. So the bit position of 1 is assigned to R1, the bit position of 2 is assigned to R2, and so on. So as you could see, the bit position basically defines what position within the string. So you can't have something like 00011, which is not a bit position. Now, each devices will also be assigned with something called BFR prefix, which is nothing but a reachable address within the domain, preferably our loopback address. So the combination of BFR ID and BFR prefix needs to be assigned for each of the edge devices. Now, once we have this assignment, the next step is to propagate this information to other beer nodes within the domain, call it as beer domain. So in order to do this, the IGP protocols like, the link state protocols like ISIS and OSPF, it's been extended using different TLVs and sub-TLVs, which allows us to propagate this BFR ID and BFR prefix. Once we have this information propagated to all other devices within the domain, the third step is to compute and populate the forwarding entry, the beer forwarding entry. So how do we do it? We basically use the shortest path algorithm or any other algorithm associated with the link state protocols like OSPF or ISIS. We identify the shortest path to the BFR prefix and associate that forwarding information directly to the BFR ID, which is associated to the BFR prefix. And If we have more than one BFR ID, which is actually using the same egress interface or same forwarding details, those BFR IDs will be combined together using a Boolean OR operation and will be created as one entry. So in this example, the node D is actually using A as the next hop to reach R1 and R2. So the BFR ID of R1 and R2, which is 00001 and 00010, will be combined as one entry using Boolean OR operation, which will be a resulting of 00011. So this entry will be marked with the next hop of A. So it's not just the edge devices, all the other devices will basically follow this to populate the BF forwarding. Again, when I say all the devices, the transit devices, they are not supposed to be, or they are not required to be assigned with a BFR ID or BFR prefix, but because they participate in BF forwarding, they are required to compute the shortest path for each of the BFR prefixes, and they populate this BF forwarding table. Okay, so let's now look into the data plane encapsulation. So for each stream, like I said earlier, we carry or we encode the set of BFR IDs together to form a bit string. So in order to carry this bit string in the packet header, there's a new header has been proposed, called as BR header. So the bit string field of the BR header basically will encode all the BFR IDs who are actually interested in receiving the stream. There are other fields in this BR header. They basically solve different purposes. Like, for example, the DSCP is used for quality of service purpose. The protocol type will basically identify what payload or what packet has been encapsulated with this BR header. The entropy is used for load sharing, and the BFR IR, or the BF forwarding ingress router, basically identifies who's the ingress device, which basically encapsulated the packet with this BR header. Now, because this is a new encapsulation, we need a way to differentiate that this packet is a beer packet, so it needs to be performed a lookup in a different table, not the traditional IPv4 or the MPLS label. So one obvious way is, of course, get an assignment from IEEE for ether type. So the ether type assigned for beer is AB37, which can be included in the ether type of the layer 2 header, which identifies that this is a beer packet. Now, not all the hardwares may support this because this is pretty new. So for backward compatibility, there's another way of doing it, which is MPLS-based encapsulation. So with MPLS-based encapsulation, you could consider this as a context identifier. So each of the devices, they assign a locally unique label with a forwarding semantic associated in a way that when the packet is received with the top label as the beer MPLS label, the action is to pop the label and perform a lookup in the beer forwarding table, not the traditional LFIB table lookup. So in order to do this, again, in addition to the BFR ID and the BFR prefixes, each devices are required to assign a locally unique label and use our IGP protocol extensions to advertise the same. So again, while in this example, we show that the BFR prefix, BFR ID, and BR MPLS label, if it is an edge device, all these three information will be assigned and advertised. If it is a transit device, we just will have the BR MPLS label advertised. Okay, let's now put these things together to see how the packet forwarding works. Once we have the table populated and when we receive the beer packet, the first step is to get the bit string from the beer header and perform a lookup in the beer forwarding table and do a Boolean AND operation. And the resulting output will be rewritten in the packet and will be forwarded to the next hop. So this way, we won't have any packet duplication. The semantic of performing a Boolean AND operation and rewriting the bit string in the header will basically allows us to forward the traffic towards different egress interfaces, which are actually leading towards the actual receivers. Again, without any duplication. So it follows the same thing, and if there are different egress interfaces which is actually which has BFR ID matching the one in the bit string, we'll perform the lookup, perform AND operation, rewrite the header with the relevant bit string, and we'll be forwarding it out. So this is a holistic view of how it works on a overall network. So imagine D is interested in receiving a stream from A. Or the source connector to A. So it uses out-of-band mechanisms like BGP, MVPN, or other overlay modes to send its interest to receive this traffic. So when it does that, it also includes its own BFR ID. In this case, 0001. So A knows that there is only one receiver interested to receive the stream. So the beer string in the data packet will set to the BFR ID of D, which is 0001. So all along the path, each of the BFR devices basically performs the forwarding lookup that we saw in the previous slide and deliver the packet towards D. Now imagine there's another receiver interested to receive the same stream. So E uses the same out-of-band mechanism to express its interest to receive the traffic to A. So any subsequent packets basically will carry both the BFR ID of D and E. So the bit string will carry 0101, which is nothing but the BFR ID of both D and E. So the packet goes to B. Because B has different egress interface which are pointing towards D and E, it basically replicates the packet, sends one copy to C and another copy to E. And as you could see, the bit string in the outgoing packet will be rewritten. So based on the lookup and the Boolean AND operation, the bit string in the outgoing packet will be rewritten. So when C receives it, it is receiving with a bit string that is instructing to deliver the packet only to D and not to E. So this way, E will not be receiving any duplicate packet because of the bit string the BFR ID in the bit string. So just to reiterate the characteristics of beer, as you could see, it's completely stateless in nature. There's no per group state entries that are required to be created or maintained in the transit nodes. Because of the semantic of performing Boolean AND operation and rewriting the header, we avoid packet duplications, and it's very flexible. So it's very flexible. The bit string, so far we saw with a size of 5 or 4, but in reality, depending on the hardware's capability or depending on the requirement, it could be 256 or 2056. Now, you have noticed that the bit string size basically limits the number of receivers because each of the bit position will be assigned to different egress edge devices. So does it mean that we can't have more receivers? Actually, beer supports more receivers, and that's where the subdomain comes into picture. So subdomain is nothing but just dividing the beer domain into multiple subdomains. It's analogous to IGP multi-area, and each of the subdomains will basically assigned with a set identifier. So a combination of set identifier and the BFR ID could be used to uniquely identify the receiver. For example, in this case, between the subdomains, we can reuse the same BFR ID. Here, A and D, they both use the same BFR ID, which is 0001. But in this case, they both have different subdomain ID or the set identifier. So for A belongs to set ID 1 and D belongs to set ID 2. So 1:0001 basically identifies A and 2:0001 identifies node D. So a combination of the set identifier and the BFR ID will be useful to uniquely identify the receiver. So this is just an example about how the set identifier can be derived based on different bit string. So imagine you have the requirement is to have, let's say 1,500 edge devices, and the example that we took is 1027. So if your hardware or the devices support a bit string of size 2056, 1027 comes well within this range. So you don't need multiple subdomains. So the default subdomain ID is, or the set ID is 0. So the set identifier would be 0 and your bit position is 1027. Now imagine another scenario where you have the bit string size of 1024. So we have 1024 and the 1027 or the BFR ID of 1027 basically comes outside this. So we need two subdomains, and in the second subdomain, we basically will get the BFR ID of 1027. So starting with 1025, it would be 1025, 26, and 27. So the set identifier would be 0 and 1. So the set identifier is 1, and the bit position is 3. So between the subdomains or the set identifier, we saw that we can have overlapping BFR ID and bit string. So the ingress is expected or supposed to send multiple copies for each subdomains. So if you have receivers in different subdomains, the ingress will send multiple copies of the same packet with a different set identifier and a different bit string that belongs to the set identifier. So in this case, we have set identifier 1 and 2 with receivers. So J, which is the ingress, when it sends the packet, it basically sends two packets, one with the set identifier of 1 and the relevant bit string that belongs to set ID 1, and another one with set identifier 2 with the relevant bit string of set ID 2. So this is an example of the underlay protocol extensions. Like I said, IGP protocols like OSPF and ISIS are extended for this purpose. These are different sub-TLVs and the TLVs and sub-TLVs that basically carries the details like BFR ID, BFR prefix, and the BR MPLS label. Okay, so use cases. I'm sure quite a few might have implemented multicast MVPN. So you'll notice that the underlay network probably have different options, like we can go with PIM, or we can go with MLDP, or even within MLDP, we can go with multi-point to multi-point, or MP to MP, or even point to multi-point, or we could go with point to multi-point traffic engineering, or ingress replication. There are different types of options, which serves different types of purpose. Now on an overlay, we can have either BGP MVPN or we could have PIM. So based on these combinations, there are like 20 plus, more than 20 MVPN profiles, which, like I said, which will be solving different purposes. Like if you're concerned about optimal traffic forwarding between PE devices, then we'll go with one profile. Wherein if we are concerned about the number of state entries that we are created, but we can compromise with the optimality of the traffic forwarding, then we go with another profile. But because all these characteristics are available with beer, we can basically eliminate the need for all these different profiles, and we can have just one profile where the underlay is beer and the overlay is BGP MVPN. So it's not just about the profile. Who has implemented the MVPN probably might be aware that the very basic requirement is on a per VRF basis, we need a minimum of one default MDT. Now this MDT, the default MDT is used to propagate the traffic to all the PE devices that belongs to the same VRF. Now, if you are concerned about the optimal traffic forwarding, because unintended receivers or unintended PEs may receive the traffic, we optionally may also have to enable the data MDT. Now, with the combination of default MDT and data MDT, we create hell a lot of state entries in the core network. Now, let's see how it is with beer. So, if we can replace those underlay with beer, all we need is, again, irrespective of the number of VRFs, all we need is just one unique bit position or BFR ID for each of those PE devices. So with this, we completely eliminate the need for a per VRF default MDT, and because beer can just define the set of receivers in the bit string, we can also eliminate the need for data MDT. So with this, in this example, if PE1 wants to send the traffic to all the PEs that are connected to, let's say, VRF red, all it needs to do is just include the bit string of all the remote PEs that are connected to VRF red. In this case, it simply will set 1110, which will deliver the packet to PE3, PE2, and PE4. And if it is intended to send the traffic only to receivers which are connected to PE3's VRF red, all it needs to do is just send the traffic with 0100 set. So this way, like I said, we get optimality without creating any state entries, so no need for data MDT. Another question, common question that we get whenever we talk about beer to different customers is, okay, do I need to enable my entire network to get beer support? Actually, the answer is no. Of course, you need to enable beer on all the edge devices so that they can perform beer encapsulation and decapsulation. But from a transit node's point of view or a transit network's point of view, beer basically allows incremental deployment. So in this case, we basically actually leverage the router advertisement capability of the IGP protocols like OSPF and ISIS, which basically includes the capability, if or not it can support beer forwarding. So when any of the node they compute the beer forwarding, they can understand if or not the next stop basically supports. For example, if I'm computing the path and if I realize that my next stop is not will not support beer forwarding, all I need to do is just identify the next available node that can support beer and create a tunnel, LDP or P2MP, RSVP tunnel, and use the tunnel to forward, encapsulate and forward the beer packets. So this way, the node that does not support don't even know that this is a beer packet. All it do is simply label switch the packet. Okay, so let's now look into the standardization effort. Beer was first proposed as a bird of feather in November 2014. We got a very good support. So a new work group was formed. Our friend Greg Shepard is the work group. I'm sure he's somewhere in this crowd. So The first RFC has been published. The beer architecture, the base architecture has been published 8279. It's basically enjoying multi-vendor support. It's a good multi-vendor collaboration. So other vendors like Cisco, Juniper, Huawei, and even other vendors are, Nokia are actually working on standardizing this effort. These are other, IETF, active IETF drafts. So ignore the first one. Actually, the first and second one are published as RFC. The other, drafts, which basically are the building blocks for the end-to-end beer, are under active, standardization. So the IGP protocol extensions, how to deploy MVPN over beer, and the beer ping, or basically the OEM functionalities are under standardization. There's also an interesting couple of drafts about how we can deploy traffic engineering in peer network. So just to reiterate the advantages. So basically, because we are using the BFR prefix, which is a unicast address, which is used to derive the beer forwarding, we basically can inherit the benefits associated with unicast forwarding to beer, like the FRR. There's no state entries on the transit nodes. It makes a very good plugin for software-defined networking, because from a centralized controller, all you need to do is just create the state entries on the ingress device. None of the transit nodes are required to create any additional state entries. So it makes it a very good plugin for software-defined networking. And on top of it, there is no multicast control plane protocol, no dedicated multicast control plane protocol for beer. Rather, we leverage our existing protocols like the IGP protocols like OSPF and ISIS. That's it. Any questions?
Lee Howard, Retevia. All of your examples used IPv4. Just checking.
Good question. Yeah. So I was using IPv4 as an example, but it supports IPv6 as well. Yes.
Good answer.
Yeah.
Hi, Aviv from NANOG. Is there any plans to do a IP underlay instead of MPLS?
Yes. So like I said, there are two ways of encapsulation. So one is using the layer 2, where we have a new ether type, AB37. And the other one is the label-based encapsulation. So the label-based encapsulation is basically for easier time to market and a backward compatibility to the existing hardwares. But yes, it can be deployed in the plain IPv4, vanilla IPv4, yes.
Thank you.
Yeah.
Okay,
All right, thank you.
thank you.